Over the last decade, a class of Alzheimer's drugs targeting the serotonin 5-HT6 receptor, specifically idalaperdine and interperdine, entered phase-3 testing. They were built on strong preclinical rationale, promising to slow the cognitive decline of the disease. They failed entirely. Across 4 adequately powered trials, nearly 4,000 patients were enrolled. The drugs failed to meet their primary cognitive endpoints. They showed 0 disease-modifying benefit at any dose on any background medication. The response to these back-to-back misses was a swift consensus. Modern neuropharmacology decided the serotonergic system was a dead end for treating Alzheimer's disease. The logic appears sound. If pushing a biological system doesn't alter the disease course, then the degradation of that system must be a meaningless byproduct, a downstream consequence of the illness, rather than a driver of it. But that clinical assumption collides with the physical reality of human brain tissue. Examine a brain post-mortem, and a highly specific pattern of destruction emerges. This chart shows neuronal loss across the brain's 4 major subcortical projection nuclei in Alzheimer's patients. Focus on the serotoninergic dorsal Raphe nucleus. At an effect size of 1.79, that depletion is 3 times larger than the loss seen in the substantia nigra. The destruction of the substantia nigra produces the devastating motor symptoms we recognize as Parkinson's disease. The Raphe sustains a proportionally massive insult and produces no recognizable neurological syndrome at all. When a structure is this heavily targeted by the disease, the field has misunderstood what the lesion actually does. We can see the error by tracking exactly when the destruction begins. The break staging system maps the chronological sequence of tau pathology in the brain, starting deep within the subcortical pretangle stages. The ordinal sequence is strict. In the largest autopsy series ever conducted, researchers found abnormal tau in the serotonergic dorsal raphe at pretangle stage C. This happens before a single tangle appears in the cortical regions associated with the disease. At Brock stage 0, before clinical symptoms, stereological counts reveal 7.9% of locus coeruleus, and 2.6% of dorsal raphe neurons are already carry tau inclusions. Mapped to a lifespan, this burden accumulates in people in their 20s and 30s. The raphe's failure marks a preclinical origin point, silently taking hold a full half-century before the first signs of dementia appear. This raises a mechanical question. Why do these 2 specific subcortical nuclei, the locus coeruleus and the dorsal raphe, accumulate tau decades before the rest of the brain, despite using completely different neurotransmitters? The standard hypothesis relies on chemistry. The coeruleus produces a highly reactive aldehyde when monoamine oxidase A breaks down catecholamines. But that specific reaction doesn't happen in the serotonergic raphe, which lacks the substrate and relies on a different enzyme isoform entirely. The true shared vulnerability is structural. A single dorsal raphe neuron operates from a soma perhaps 20 micrometers wide, yet it maintains a highly collateralized, unmyelinated axon that stretches nearly 19 centimeters in a rat and far longer in a human. This massive cellular footprint is constantly stressed. The neurons are autonomous pacemakers, firing continuously and sustaining a permanent calcium load. Worse, they entirely lack the aggrecan-based perineuronal net that shields other neurons from extracellular tau. Because tau's primary effect is destabilizing microtubule transport tracks, this geometry is fatal. When a cell depends on a transport line hundreds of thousands of times longer than its body, a tiny disruption in the track starves the extremities. The arbor dies from the outside in. The human patient notices nothing at all.
Because the raphe broadcasts serotonin into the extracellular volume rather than wiring to discrete synapses, surviving axons simply sprout and pump out more transmitter. They hold ambient concentrations steady while their neighbors die. The raphe is uniquely doomed by its structural dimensions and missing cellular armor. Because the brain masks this structural decay for decades, clinicians only observe the late-stage result. This created a secondary bias, the assumption that losing the serotonergic raphe simply causes the severe depressive symptoms often seen in advanced Alzheimer's patients. This 2004 postmortem matrix plots dorsal raphe neuronal density across 4 groups. Look at the Alzheimer's subjects. Those with and without major depression show the exact same severe depletion. Conversely, patients with primary depression exhibit 0 structural cell loss. Whatever catastrophic consequence this lesion has on the AD brain, it is fundamentally not depression. So if the Raphe isn't in plain memory, and its destruction isn't driving depression, what exactly is the brain losing? It is losing a systemic biological break. The answer lies in how serotonin interacts with the cortical cells it innervates. The system relies on a specific molecular pathway, the GS-coupled 5-HT4 receptor, and its physical association with an alpha-secretase enzyme called ADAM10. When serotonin binds to the 5-HT4 receptor, it drives ADAM10 to the membrane to cleanly cleave amyloid precursor proteins. Withdraw that constant serotonergic tone, ADAM10 retreats, and pathogenic enzymes are left to form toxic amyloid beta. Clinical data proves this mechanism operates in living people. By manipulating this exact serotonergic pathway in healthy human volunteers, researchers altered the cerebrospinal fluid production rate of amyloid beta by nearly 40%. The early architectural death of the Raphe removes a systemic restraint across the entire cortical mantle. It is a permissive lesion. The break fails silently in the third decade of life, leaving the cortex defenseless against unchecked amyloid accumulation. We can now return to the failed Phase 3 trials of the 5-HT6 antagonists. The field looked at those negative results and abandoned the serotonergic system. But look at the trial design. They tested drugs built as symptomatic cognitive enhancers, aiming to boost neurotransmitter release in already demented patients with established degenerating circuits. This timeline charts biological progression against clinical intervention. The Raphe withdraws the amyloid brake in the patient's 20s and 30s. The pharmaceutical trials enrolled patients in their 70s and 80s. You cannot engage a preventative mechanism in a brain freely depositing amyloid for 50 years. The pharmacology targeted the signaling of a dying cell half a century after the therapeutic window closed. A hypothesis that relies on mistiming to explain clinical failures must establish exactly what evidence would falsify it. First, we need a true prevention trial. Administer a 5-HT4 agonist to cognitively normal middle-aged adults at elevated risk. If restoring that tone produces no effect on long-term amyloid accumulation, the permissive brake model collapses. Second, we need prospective biomarker tracking. We need an imaging tracer capable of resolving the dorsal raphe in living people to see if its structural integrity in midlife accurately predicts downstream amyloid production rates. The word raphe translates from Greek as a suture or a seam. Anatomically, it is the line where the two halves of the brainstem meet in development. Biologically, it is the system that sets the baseline parameters for the entire forebrain. A seam is only noticed when it gives way. In Alzheimer's disease, it gives way silently. By the time we notice the fabric of cognition tearing, we are decades too late to simply reinforce the stitching.